Hi folks, we're going to do some Doppler effect problems right now. Number 23, an airplane traveling at half the speed of sound, 172 meters per second, emits a sound of frequency 5,000 hertz. What frequency does a stationary listener hear as this plane approaches? Okay, here's our Doppler equation. The frequency that is observed is equivalent to the frequency of the source times the velocity of the wave in the medium plus minus the velocity of the observer, the velocity of the wave minus plus the velocity of the source. So I want to know what frequency is going to be observed. The frequency of the source, well, this airplane is producing a 5,000 hertz sound. When in doubt, we're told in our problems for the velocity of sound in air, use 343 meters per second at 20 degrees Celsius. And this is an approach. So when our observers or the two sound-making devices are going towards each other, you use the top set of marks in this equation, the plus on the top and the minus down below. So this is going to be, I'm sorry, I'm getting a little crazy with my pen here. So this is going to be 343 plus the velocity of the observer, and the observer is stationary, so plus 0. Velocity of sound again, 343 meters per second, minus the velocity of the source. The source is 172 meters per second. And we have to then simplify this equation before we actually subtract or do the multiplication. So take this one step at a time. I am going to, you can do it all in one go in your calculator if you're good, but I want to just piece this out in case somebody gets lost. So 343 on top, and then down below 343 minus 172, so the bottom is 171 meters per second. These units will cancel, so I'm going to end up with 343 divided by 171. So I'm going to end up with 5,000 hertz times this fraction gives me 2.0058 and change. You can carry the numbers through till we get to the end with Siggy Figgies. So times 5,000, and I am going to observe, the observer is going to actually hear 10,029 hertz. That is going to be the observed or heard frequency due to the Doppler effect. Because it's approaching at such a high speed, the frequency is going to go up. Always do a reality check. Does that make sense? Yes, it makes sense. All right, number 24. Here goes. Problem says the predominant frequency of a certain fire engine siren is 1550 hertz. What frequency do you detect if you move with a speed of 30 meters per second away from a stationary fire truck? So frequency observed is frequency of the, I'm saying this, frequency of the source, velocity of the wave plus minus velocity of the observer, velocity of the wave minus plus velocity of the source. So what frequency do you detect? So frequency observed is what I want to know. Frequency of the source, the fire engine is producing 1550 hertz. And the velocity of sound in air, we're not told anything about temperature or any weird situations, so we're going to use our 343 as our standard value for 20 degrees Celsius. Now, what frequency do you detect if you move with a speed away from the stationary fire truck? Because this is an away situation, you use the bottom set, so this is going to be a minus on the top and a plus on the bottom. The velocity of the observer is going 30 meters per second away. Sound is 343. The fire truck is stationary, so it has a speed of 0. So I'm going to simplify this down, 550 hertz. The top of the fraction, 343 minus 30, so 313 meters per second, divided by 343 meters per second. Divide, multiply, what do you get? So 313 divided by 343 times 1550. I end up with 1414 hertz. Always stop and reality check. Does that make sense? You're moving away from the source of sound. Frequency is going to go down when you're moving away. Yes, that makes sense. Let's do another one. One of the original Doppler experiments involves a tuba that is played on the back of a moving flat train car at a frequency of 75 hertz. And this was actually an experiment done by Doppler himself to try and understand the Doppler effect. A second identical tuba is played at the same note while at rest in a train station. What beat frequency was heard if the train approached the station at a speed of 10 meters per second? And this is one of the ways that Doppler could detect very slight changes in frequency, is he actually looked at beat frequency. So what we have to know is, for a beat frequency, we have to know those absolute value of the two frequencies. And this is what we ultimately want to find out, is we want to find out that beat frequency. Well, we know one of these frequencies is going to be the at-rest frequency, 75 hertz. And before we can find the beat frequency, we have to find the other frequency that is produced by the moving tuba on the train. So let's go back and find that out. So I'm going to find the frequency observed from the moving tuba. I always think it would be a cool experiment to reproduce because it would be pretty nifty. Okay, so let's go back to our Doppler equation. The frequency observed is going to be the frequency of my source. Velocity plus minus velocity of the observer minus plus the velocity of the source. So what do we have here? Frequency of the source. I said the wrong thing. This is frequency of the source. Frequency of the source is 75 hertz. The tuba is producing 75 hertz sound. The velocity of sound on that day. Let's take a double check here. It says nothing about temperature, so we're going to go forth and use that 343 meters per second. Now, the train is approaching the station, approaching. So this is a towards situation. Because it's towards, we're going to use the top set of values. So plus velocity of the observer. The observer is at the train station. That's going to be 0. Down below, 343 speed of sound minus the velocity of the source. The train is moving towards us at 10 meters per second. So 75 hertz. Our fraction, 343. Down below, 333. These are each meters per second. And let's do the math, see what we get. 343 divided by 333 times 75. I end up with 77.2, round it off to 0.3 hertz. If I want to keep it to 3 decibels, that is going to be the frequency that is observed. I can then take that, push that back up in here to 77.3 hertz, and now I can calculate beat frequency. So my beat frequency is going to be 77.3 and 75 minus, and we're going to take absolute value, so my beat frequency is 2.25 hertz is my beat frequency. So that should give me that. I'm just going to double check I didn't do something silly. No, that's what I got when I did it before, so life is good. Okay, that will do for this set. We got another couple Doppler problems to go. We'll see you then.